Now we can generalize the situation. Our general situation is y double prime plus omega naught squared y is going to equal some maximum force times the cosine of omega 1 t. And it's a little careless of me to put a force here. It's actually a maximum force divided by the mass of whatever the system is. So I'm going to put a big M under my F max here and here. And I guess I'd better put one here as well. Now, to generalize though, this is going to be our equation. And we can solve this equation and let omega 1 approach omega naught. And what we're going to get symbolically is going to explain what we got here. It's going to mimic what we got in the preceding, where we did this for specific frequencies. And you're going to see symbolically how resonance is, how we approach resonance, and get a deeper understanding of how all that occurs. The symbolic solution ends up giving us a better picture than any numerical solution would. Okay, so we're not going to do that in class. Your book does it. You can refer to your book if you like, but I do recommend that you set it up and do it yourself. Okay, well, we could also set up the system where the driving frequency is equal to the original frequency. If we do that, we get a fundamental set that looks something like this, except I appear to have left the t off of the sine of omega naught t. I included it here. I didn't write it down when I wrote down the fundamental set. So your particular solution will be, and actually we're going to have to have t here too. Okay. The fundamental set for the homogeneous equation is this. Our solution for the non-homogeneous equation is going to be this. Actually, I didn't need the t in here because the fundamental set just applies to the homogeneous equation, and this is it. So I was off when I said that. Okay, the particular solution. In order to get a particular solution, you can't just use a combination of sine and cosine of omega naught t, which is what we would do if we had an omega 1. We just use a combination of omega 1 t, sine of omega 1 t, and cosine omega 1 t. Here, we have to use a linear combination of t cosine omega naught t and t sine omega naught t. We plug in, solve for a and b, and we're going to have some combination of these. And it's going to be yp is ct, say cosine of omega naught t, plus some phase angle. I don't want to say too much because I say you should interpret this, but I'm going to go ahead and say this anyhow. As t increases, obviously, then the amplitude of this cosine increases linearly without bound. So what do you get? You get a solution. It starts out as a nice, well-behaved cosine, but it keeps spreading out in a kind of a linear envelope, and you get this resonance phenomenon again. And that's due to the t. And you should understand very well what happens when you multiply t by a cosine of something, the cosine of a product of t. In any situation, you do have some drag, so you do end up with an equation like this, and the solution to this equation explains how the resonance gets limited. If you have a small delta, then the resonance can, the amplitude of your solution can grow pretty big before this starts to take over. And if you solve this equation and consider what the solutions tell you, you'll see how that works out.